Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Originally had about 3 talks in this session, but we are fortunate to have another prolific researcher, Dr. Jeffrey Palmer from MIT. So we've decided to include a 4th talk in the session. As a result, every talk is going to be about 20 minutes, and but we'll still have time for questions, 1 or 2 questions in the end. And we basically have about 4 talks. So with that, I want to start and introduce our first speaker for the session. Professor Roozbeh Jafari. Professor Jafari is an associate professor in biomedical engineering, computer science and engineering, and electrical and computer engineering at Texas A&M University. He received his PhD in computer science from UCLA. His research interests lie in the area of wearable computer design and signal processing. He has published over 140 papers in this area and has served as a general chair and TPC chair for several flagship conferences. He is a recipient of the NSF Career Award, the ARTAS Best Paper Award, and the Andrew Sage Best Transactions Paper Award. He is an associate editor for the IEEE Sensors Journal, IEEE IoT Journal, and the IEEE Journal of Biomedical and Health Informatics. Today, Professor Jafari will talk about connected wearables as computing devices on the edge of the cloud. So please welcome Professor.
Okay, so it's an honor to be here. Thank you very much, Tribe, for inviting me. So I am going to talk about some of the projects that we have related to wearables. But before we do this is one of the oldest wearables, right? So the definition, what I have in mind when I talk about wearables, are computing devices that are attached to us, not because we want to carry them, but because either they have sensors that are reading from our body, or they have actuators that are giving feedback to us, right? So this is one of the older wearables, watches. So this is a question I have for the audience. What do you think this ad is trying to convey here? What is the message of this ad? You know, you have George Clooney showing his expensive watch on his boat in Switzerland. Are they trying to tell you that you need to purchase one of these wearables because you need it? Probably not, right? So when you look at the evolution of wearables, we've got to the point with these expensive devices. These devices are used mostly to essentially exhibit a sense of power, a sense of wealth, right? People are going to buy these devices not because they need them, but because they want them, right? But it's interesting when you look at actually the history of watches. We used to have pocket watches for about a century, and they were already small enough that people could actually strap them on the wrist. But the society didn't want to do it at that time, unfortunately, because it was mostly male-dominated, and they felt that if you happen to strap a watch on a wrist, that would be essentially feminine. They didn't want to do it. It wasn't until World War I where soldiers had to actually do this. Because when you are in a war field, when you're using the watch to essentially the time to synchronize yourself with the rest of the team members and the crew, it would be much more challenging to get the watch out of the pocket. It would be much easier to look at it on the wrist, right? So this device came out of necessity. There was a need for it. And then it has essentially traveled to get to something like this. When we look at cell phones, right, the very first generation of iPhones, I think one of the reasons that these smartphones became so successful, in addition to having a nice user interface, was the fact that these devices are fully programmable. You can find apps that can improve your productivity. The apps can actually work as an office for you. You have apps that would help you with social networking. You have apps that would help you listen to music, all of it. It's actually interesting. When you look at these devices, we still call them a phone. But think about what portion of the day you're using to actually talk on this device. I rarely talk on my phone, right? I'm using it for a whole bunch of other purposes. And I think the reason that this happened was that it was a fully programmable device. and we gave it to the hands of the users, and the users can actually use their creativity to build a whole bunch of other use cases for these devices. Okay? So our thinking is, when we look at these wearable devices, there are a couple of unique characteristics. These devices are in direct contact with our human body. If I'm wearing a computational device that is supposed to do something, because I can look at it all the time, I can see the response of it all the time. I am in the loop with my computational device all the time. I can identify errors pretty quickly. Often when we are looking at these devices that are used for sensing, for various applications and various tasks, it's interesting that these sensors, if you use them in isolation, if you use them in a lab, if you use them, let's say, in a clinic, most of the time they work well because they are used in a controlled environment, they are operated by experts, and we can reduce the chances of error. Whereas when we place them on the body and you send it to the homes with the users, the sensor could be misplaced, the sensor could be faulty, the user, the operator may not use it properly, or the signal processing may not exhibit the required level of robustness in that environment, just because that environment is not controlled. The power, computation, and resources and the connectivity have very unique requirements. These devices are often, this device can last for about a day, this device lasts for about 7 days. When you look at the form factor of these devices, the battery is going to be very small, so there is not really any comparison to what we have on a smartphone. The connectivity of these devices, often, this phone is used as a hub. These devices, for security reasons, they cannot go directly to the network. And you have a resource-constrained computational platform on these devices. And then the other unique characteristics of these devices is that when you look at these systems, think about the notion of cell phones that we talk about, right? Now you want to build the next generation of programmable platform for these wearables. Your application area is going to be much broader compared to what we have in a cell phone, because now you're dealing with individual users. You're trying to customize the applications for the individual needs of the users, and it's very diverse. So those are some of the unique characteristics. I want to talk a little bit about some of the work that we do in our lab. So we do system development quite a bit, prototyping. We are really good at building devices in a small form factor for a specific application. So here is one example where, we're good at, we are doing bioimpedance spectroscopy. We take this device and we create this small watch form factor. This actually became a reference design for Texas Instruments. They are selling it on their website. This device can measure the blood pressure. I'm going to talk about it in a second. This device is essentially our motion sensor, but the academic version of it is fully open platform. You have full control over various wireless communication protocols, and then a number of sensors, including accelerometers, gyroscopes, and magnetometers. What we do is we look at new sensing paradigms quite a bit. It's interesting, when we look at sensing from human body. Let's consider one example in medicine. We have a number of physiological measures that medicine is used to. For example, electrocardiogram or blood pressure. One of the reasons that medicine is using these devices or these sensing modalities is because we had a tool that would help us to measure something like electrocardiogram. You place 2 electrodes on the 2 sides of the heart, and you measure essentially the electrical activities of the muscles of the heart, right? And from that point on, you try to do the diagnosis on a disease. So that's great, but that doesn't mean we should stop at that point. We might have new sensing paradigms and new sensing modalities that with wearables, we can do them very efficiently, but the field of medicine may not know how to interpret them, right? One example is a pulse transit time. I'm going to talk about it. So we look at sensor development for new sensing paradigms, but considering the wearability of the devices. We look at robust signal processing quite a bit. It's important to think about these devices as, it's interesting when you look at this device, which is a keyboard, right? This has been around for about a century, since 1873. We used to have typewriters. This is still the primary modality for us to talk to the computers, right? What is the reason for that? Because it's extremely predictable. It's extremely robust. Once you hit A, you're going to get A 99.9% of the time, right? So if you're dealing with these devices, And if you're building applications, if you're not dealing with 99.9% precision and recall, probably the users are going to be frustrated. And then the last part is some of the analytics that would go into the cloud. What kind of services are we going to have for anomaly detection? What is a Google for these? Or what is a good search engine for these wearable devices? So I'm going to show you a couple of videos. And I want to make sure that I don't go over my time. So here is an example of an activity recognition system that has been around for a long time. You know, Professor Paradiso is one of the experts actually in this area. He's sitting, and I'm looking forward to his talk. For this work, what Gian wants to do is he wants to build activity recognition algorithms that would operate irrespective of the placement of the sensors. When we are dealing with activity recognition algorithms, we're dealing with a number of sensors that can measure physical phenomena like acceleration and gyroscopes. And the way we take those measurements is it's a function of how you place them. So the idea here is that what if he would just throw one of those sensors in his pocket, irrespective of how the sensor is placed? What if these sensors happen to be a ring that could be placed in any direction, right? And then the system can still perform the signal processing. So this is one example where, you know, he is actually placing one sensor on his thigh, one sensor on his ankle, and he is doing a number of movements, and the system can actually detect it. The system is extremely robust. We are looking at about 99% accuracy. And what we do is we combine a combination of algorithmic techniques with dynamic time warping to achieve this. And you know, this video is going on. Here is another example of another wearable device that we've been working on, brain-computer interface. So for this specific project, the objective was actually to create this EEG system that would be small. It's the size of a credit card. Some of you who may have been working with EEG systems might have seen the larger, chunky systems that are the size of a desktop. The electrodes are often wet contact electrodes. What that means is you know, it takes time to set it up. It takes about 45 minutes. You're going to have to place the electrodes, add salt water to build a good contact. This system uses dry contact electrodes. We use a number of intelligent techniques to basically configure the quality of contacts, and then you know, the acquisition system is the size of a credit card. So the application for this is actually for the ICU patients. In ICU units, often patients, they have so many devices attached to them, and it's hard for them to communicate with the outside world, right? The nurses would have to bring these, what is so-called communication boards, and point to different you know, figures on this communication board and try to find out, you know, what the patient wants to do at that time. So what we thought we would do was to actually use the notion of brain-computer interface to help them. The notion of brain-computer interface is, you know, essentially you think about something, we try to directly decode it from your brain. And the specific paradigms that we used here is, if I show you an LED that is flashing at 6 hertz, when you look at it, we can capture that 6 hertz from the occipital part of your brain, the back of your brain, right? Now, if I happen to show you 2 LEDs, one is flashing at 6 hertz, one is flashing at 10 hertz, the moment that you look at one of them, I can find out which one you're looking at. So in this example, you know, there are multiple boxes on the screen. Do you have a question? Are you in pain? Or you want to go back, and you know, the patient is expected to look at them, and the system would essentially capture this after a few seconds, in this case 4 seconds. And then, you know, so I'm in pain, how much pain you have, and so on. So one of the technical challenges that we are dealing with for this system is, and I'm going to try to be quick here, is that every time we're dealing with wearables, the interface between the wearable and the body becomes really important, especially when we have a sensor. You know, think about having optical sensor or electrical sensors. You want to have a perfect contact with the skin, right? But you cannot guarantee that perfect contact at all times, because we are moving around. You know, you might start sweating. Sometimes you place an electrode, and then underneath the electrode you have hair. So the idea here is that, you know, think about these electrodes as individual electrodes, these fingers. If we happen to try to measure the quality of contact, and the way we do this is that we use the common mode voltage as a background. We inject a reference signal, and we try to measure how well we have impedance matching between the positive and the negative. If we happen to measure this continuously, as the conditions change, I can pick and choose the best set of fingers in the interest of increasing my signal-to-noise ratio. So this example is showing essentially the quality of contact. So in this experiment, what we did was we placed one of these electrodes on the forehead, and we placed a wet electrode right next to it. The wet electrode is giving us the reference signal, right? The wet electrode is here, and this is the shape of the signal that we are seeing. We asked the person to actually close his eyes. So we see this 10 hertz, which is the alpha rhythm here. And the wet electrode is giving us this 1/f noise. It's a beautiful signal right here. And then the rest of the electrodes, they are giving us a varying quality of signal. You see that the yellow one is actually giving us a very poor signal quality for various reasons. It could be that there is a hair underneath. And then what we noticed was that if we happen to measure the signal, the contact quality, if we sort them according to this order, and this is essentially the sorted order, you would see the exact same sorted order in the signals that we are capturing, right? So this is one example, and as you do this, you can actually improve the signal-to-noise ratio by 40%. But what that means is that you can actually capture things much faster. Okay, so I have 5 more minutes, and I have about 10 more slides. Okay, I'll try to be quick. So here is one example, the BioWatch that we built for Texas Instruments. What this watch does is that it measures the blood pressure directly from the wrist. And the way we measure that is that we measure the ECG when the heart is beating. We also measure when the blood arrives here. We measure the time difference between these two events, which is called pulse transit time. That's actually pretty easy to measure. And then we translate that into the blood pressure. So when you do things of this sort, we talked about the robustness of the signal processing and the robustness of the sensing. It's interesting that we are building it for an everyday application. So the person might be driving, the person might be playing tennis, all these activities. When you're not moving around, you have this beautiful signal, which is your PPG, and that's your heart rate. You take the frequency, the power spectral density of this. You have this beautiful 70 beat per minute. That's your heart rate. The moment that you start introducing motion artifact, in this case running, you see that the heart rate is actually hidden here, but you have a whole bunch of other principal frequencies that are not your heart rate. So one of the problems is how to actually remove those motion artifacts and the sources of the noise. So this is, again, you have an ECG signal that is a clean signal, and then with the noise, you start having all these extra peaks that you don't want. The other aspect is, so when you look at the wearables, often we can actually capture the physiological phenomena that we are trying to capture from different sources. Think about the next generation of cars. I'm pretty sure that in the car seat, there is going to be a heart rate monitor. Once you sit in there, you're going to be able to capture the heart. You can capture the heart rate from your glasses. You can capture the heart rate from these Apple Watches, and so on. So there are multiple sources of signal that can actually give you that physiological phenomena, but they might have a varying error or varying robustness over time. So here the idea was that let us think about a heterogeneous set of sensors. Let us use the notion of particle filters to basically capture something like a heart rate. So to just give you, in the interest of time, I won't go over the formulas. But so the particle filters, the way they operate is, I'm just giving you this example. So there is a robot sitting somewhere in this room, and the robot has essentially a sensor that measures all the obstacles around, right? At the beginning, you don't know where the robot is, so there is one single observation that you get, and that observation is what is the proximity of the obstacles to the robot. And that would give you essentially a whole bunch of options in the room. And then as the robot starts, okay. So so at the beginning, all these particles could be essentially a potential solution. And as the robot starts moving, it converges because there is so many unique solutions there. And as you can see, as the robot starts moving, these two particles become more important because they both actually fitting the solution that we have. The moment that the robot enters this area has unique characteristics that is not present here. And that particle quickly goes away. So that's the whole notion of particle filters. And so the idea that we have it, again, in the interest of time, the idea that we have here is that you might have multiple modalities of signals. So this is a PPG. This is an ECG. In ECG, when you're trying to capture the heart rate, you measure the R to R peak. In ECG, you might measure these. In PPG, you might measure these peaks. You might look at the higher slope of the signals here. And let us look at those as an operator for these particle filters. Let us combine them all and see which one is giving us the most consistent answer. So the way this system operates is we have particles that are essentially giving us the states. Those are the heart rates. Each of those states have a weight. Then what we do is we take a measurement, and based on the measurements, we try to adjust the weights of each of those particles. Then we do the resampling. So these are potential candidates for the heart rate. We take the observations, we adjust the weights, then we do the resampling, and then at this point we propagate the particles, and then we measure the posterior probability to measure the heart rate. So at any time, the way this system operates is at any time, you look at one time that you're taking the measurement, you look at the window before, you look at the window after, you try to basically calculate, for example, the R2R intervals. All possible scenarios. You don't have to worry about having a false positive. And you add all of those to your particle filter framework, and you let the particle filter framework decide, what would be your heart rate. So that was one example for ECG. For PPG, this is, again, the PPG signals in the frequency domain as the person is moving around. These are the components that correspond to the noise. This is the true heart rate, and then this is a clean heart rate frequency. Often for these systems, we also have additional sensors that give us only the noise. So I have a PPG sensor, I have an ECG sensor that gives me signal plus to noise, right? And the sensor can get as good as it gets. But then let me add additional sensors that would only give me the noise, and then let me figure out how I can remove it, right? So I know that accelerometer cannot give me the heart rate, right? So in this case, the accelerometer is giving me something like this, and then surprisingly, I have that on the PPG too, so I know that's not really what I'm looking for. So I won't go into the formulas in the interest of time, but to just give you a quick overview of how this works is, this is the this is the state that we have. These are our observations. Observations are coming from ECG, PPG, accelerometers. We combine all of them. We measure the posterior probability, and from that point on, we measure the heart rate. So it's interesting, actually, when you look at these, and these are a condition of experiments where we have PPG, ECG, and a combination of those. In some cases, and in some subjects, one of these modalities or both of them work. In some cases, for example, for subject number 2, this is giving us a very bad error, 43 beats per minute, right? But the ECG is working relatively well. When you combine these two, you could see that actually the particle filter is extremely robust in eliminating some of the error that comes from one specific modality. So the robustness of the signal processing is extremely important. I feel the context is extremely important. You have a single sensor here. There is so much you can do with this. But the moment that you start fusing this with other modalities in the environment, you can potentially get a lot more information for application development. Wearables know quite a bit about our life, our activities, our habits. So I think this can essentially accelerate the rate of application development beyond what we notice with the smartphones. They are extremely personal. It requires deep customization. And the last part is, which is sort of very close to my heart, is I would really like to be able to actually empower students to play with these devices and build the applications that they like. And we sort of go beyond smartphones, because with the smartphones, what we have is we have a programmable platform, but this platform is fixed. With wearables, we need to actually add programmability on the hardware side too. So this is a quick video. This was a student project that actually started getting quite a bit of publicity, and I would let you watch it.
Communication is a fundamental part of life. No matter who we are or where we are, our humanity never shines as bright as when we express ourselves. Our exchanges make us who we are, but the communication challenges faced by those who are deaf and those who are seeking to understand them can sometimes limit these exchanges and reduce the overall quality of life for everyone. What if it didn't have to be this way? What if the deaf could communicate with those who don't know sign language and be instantly understood? Rouzbeh Jafari, a biomedical engineer at Texas A&M University, is developing the technology needed to make this a reality.
We are building a wearable system that can identify and detect the sign language. The wearable system uses two different sensing modalities. It looks at the hand movements through motion sensors. It also looks at the muscle activations to identify specific types of hand movements. This device will overcome the communication barrier between those who know the sign language and those who don't. The current prototype that we have has microelectronics placed at different parts of the hand. Our ultimate objective is to reduce the form factor to a watch, so the system will be truly wearable.
It's engineering with the power to empower, and the technology could make a world of difference to each and every life it touches.
So thank you so much for listening to my talk. And it was interesting, the reason I showed that video was that it took about 3 weeks for my students to put together that system. Just because, you know, we had everything as an open platform, we just gave it to them, and it led into an interesting and a very, very nice project. So I guess I just went over a little bit, but if there's any question, I'll be happy to take them.
So thank you, Professor Jafari, for telling us how connecting wearables increases their robustness and the richness of the decisions they can take. Thank you again. So our next speaker is Professor Joe Paradiso from MIT Media Labs, where he's a professor in media arts and sciences. He has directed the Responsive Environments Group at the Media Labs for the past 20 years. He is a well-known researcher in this field. His current research explores how sensor networks augment and mediate human experience, interaction, and perception. He received his PhD in physics from MIT and a BSEE from Tufts University in 1981 and 1977, respectively. He has an extensive background in sensing, processing, and control systems. He has published over 250 papers and 17 patents. He is a member of the APS and ACM and a senior member of the IEEE and AIAA. Today, he will discuss how to have fun with interconnected wearables, emphasizing the role of interactivity, energy, and data communication. I'm sure it'll be a fun talk. Please welcome Professor Paradiso.
Thanks a lot. It's great to be here at MSR and talk to you a bit about what we do in my group. I'm going to be going very quickly through some stuff. If you want more detail, you can always contact me or go to our website. This is what I'm going to try to cover. I'll blaze through a few older things that kind of set the context, and then lots of applications of wearables, built environment, a lot of UI stuff, some stuff in the static and robotics. If there's time, I might talk a bit about stuff we're starting to do on extending perception and presence and with sensor nets, feeding sensor nets into wearables. This is, after all, the home of the HoloLens, so that stuff gets very relevant. Why did my screen go to sleep? Well, maybe it's still working. It's still working. Good. This is a historical project. Some of you know this, probably a lot of you don't. Go through it quickly. It's my first wearable that I ever really built, 1997. A shoe for a dancer for the first ISWC Wearables Conference. Measured 16 parameters per foot and broadcasted out in real time, updates at about 60 hertz from a base station where it would make real-time music. When I would go through the list of sensors I had on the shoe, back then people would laugh. But now it's the way it's done. We had to build custom radio protocols to do it. There was no Bluetooth, there was no standard radio protocol that could do this. We had to use our own radio for this. This is a quick video of a dancer using the system. The music is coming from a rack of synths with an interpretation of his sensor data happening in real time on a PC. So he's driving all of that. It's back in 1998. This was one of the inspirations for the Nike Plus. Nike were sponsors. They hung around with us a lot at that time. And it hints at something that goes well beyond that, I think, that we still haven't quite achieved. We have sensors to measure gesture that are commonly now part of our wearable rig. We talked about Fitbits. There are all kinds of other things that we can wear, simple sensors. Once a famous artist does a piece for gesture interpretation, then in order to hear it, you'll have to exercise. So I think there's a whole world of entertainment waiting for wearables here that we hinted at in this old example. We went on then to do a gait analysis with Mass General Hospital in collaboration with them way back in the early 2000s. We had a stacked sensor array over here, that we developed for that purpose, our own custom radio protocol again. At that point, we're thinking about what people call shields, right? You have a generic sensor, you just put stuff on top. But my students didn't like this at all. They kept, this is the only project we've used it in, because for a wearable, you really want to customize it and make it small. It's hard to make a generic architecture you can just plug things into, right? It doesn't want to be modular so much. So this is the first and last of its kind. This is one of the next projects we did. Again, it's just a card all by itself. It's for athletics. We met the doctors for sports medicine at Mass General through the people doing gait analysis. This is for professional baseball players. We did it in the mid to late 2000s. Very, very high range IMUs, 10,000 degrees per second, gyro, 100 Gs, sampling at 1 kilohertz. We'd have a fast radio network to synchronize everything. Again, there's nothing available. We had to build it ourselves. You start to see product in this space now, but still typically for 1 or 2 sensors, not for a whole ensemble of them. Here's a famous baseball team you may know. We worked with them pretty closely for a while, sensors strapped on the athletes. And in this case, the later versions, we store data to flash, synchronize with our network, and then take the flash out at the end of the day, dump it, and analyze the data with the doctors. While we're in spring training, nice and warm in southern Florida, my student Mark Fellmeyer was pretty uncomfortable in New England, so he was frustrated with this. And it's a topic that came up in some of the talks earlier. The good thing about a wearable is it's a first-person measurement. It's a measurement right at the location of the user, on the user, not something on a wall that you're trying to infer something like comfort from in this case. So thermostats, even though the Nest is very nice, aren't really measuring what a wearable can do. So we built one. This is a device that Mark put together. It's got a motion sensor running at very low power using passive analog accelerometers back then, before you get the low power digital ones. It had temperature, humidity at the wrist, light levels, and we could infer what office you're in from the radio. Once a minute it would upload its data. You could label if you were hot or cold. And the thing would last about 2 years on a coin cell, so very, very low power. This is a switch curve everybody got. You basically would see the data labeled as too hot or too cold, and you'd find a decision boundary in between, and you'd heat or cool the room according to it. It's not a flat line of temperature at the wrist. It's an enthalpy space closed curve, and it can be customized for individuals as they were saying hot or cold. It would adapt. We controlled the HVAC dampers with it. We could open and close a window, and it tended to work. So during a summer in Boston, around 2010, we ran the thing. We used about 25% less energy when we turned it on, similar conditions all the way across, and people were more comfortable. So it seems like it works. We moved on to lighting control. It's a lot of work in the group now is going around lighting, at least with building systems. And it's an exciting time, because this is our light switch in the Media Lab now. God forbid in this building, in this room, there's probably something similar, if not worse. It's almost a fuse box metaphor, right? These are sliders. They control some fixtures somewhere, and you have to write down some preset that you program in, and no one ever does that. So it's totally broken, even though I can control any set of lights in this whole large lab space. So we're ready for lighting control because the networking is there. We just don't have the UI. So we have a few things we did. One is a wearable, again, trying to put everything together on the wrist. We called it the wrist K. We have a full IMU on there. We've got a sensor to look at how much light comes from individual fixtures from demodulation. We have a precision pointing, precision location sensor. We're going to use the Qualcomm Peanut, but couldn't deliver it in time, so we used the Ubisense, so we could track this around within centimeters. Indoor location is going to be critical, I think, for wearables, especially in built environments. So we could see where you are. We could get the vector from the IMU, extrapolate it, and see what you're pointing at. And this is a video that Home Garden TV did about it.
The future of home technology is jewelry. Well, sort of. In the future, you're going to be able to control and monitor everything in your home wearing a bracelet like this. I'm assuming there's something very smart going on inside here.
We see this kind of the universal remote control for the smart home in the future.
Just point at the lights that you want to control.
Okay. Ooh, I turned them off. Okay, this is amazing. How is this working?
So this is tracking the motion of your wrist as you move around using the same sensors that you'd find in a cell phone or a video game controller.
Right, because cell phones sort of know when they're being tilted. If that's not a home of the future, I don't know what is.
So that's all propaganda there, I guess. But in principle, I think pointing is a natural kind of interaction that will happen from the wrist. Right now, the wrist is used for UI as a peripheral to the phone, but it's a touch screen, right? And this is kind of a small touch screen. You can do some things. But natural stuff like pointing, moving the fingers, these are things you can get from the wrist. I'll give a couple of other examples. My student Nan has been wearing a camera for about 3 or 4 years here at the Media Lab. This is her when she's doing her diploma. And then you can look at reflected light and adjust lights automatically to compensate for the light that's coming in. So she's been now in the last year or two using Google Glass for the lighting work. And we have also taken a room. We've got a state-of-the-art Philips lighting system in the room. We can light it over a very wide range. We've shown users a bunch of presets. We found the principal axes that unite those presets. So those turn out, if you take the top 2 principal axes, to be the most human-centered axes for lighting control. You can get any kind of lighting you want in this room just from those 2 axes. So initially she ran it on a smartphone. So these are the 2 axes that Nan's study has found. So one is focus. The light tends to be colder. Then it's casual, it's warmer. And this affects spatial degrees of freedom, not just color, temperature, and intensity. They're all correlated in this PCA. And pretty much anywhere in that plane you can get the lighting you want. But yeah, why use a control? Just drive it with wearable. So here she's using Google Glass to close-loop control this using her axes. So it sees how much light is coming into her glasses. And as she's moving, it's adjusting the lights of the room to compensate. So she's getting the right light where she is, doing the best it can. But then it recognizes activities, gets context. She's on the phone, it recognizes that, so it's fading into casual. So this is more appropriate for talking to a friend. And she goes back to work, and you're getting into focus again. But then a friend will come in a second. It recognizes that by how she's moving, how she's talking, and goes back to casual. So again, context will be leveraged heavily in things like this. Light switch is going to go away for sure. A lot of our recent work has we've been thinking about doing more than just lighting, trying to take the essence of a space into this room where we've got a lighting system of our own, an agile lighting system, but also we put a projection system in there to try to take the essence of, let's say, a library, a coffee shop, and bring it back and have it automatically come up relative to context. So we sampled a bunch of places around Cambridge, sampled the lighting, gotten video, gotten audio, and then we're driving it with sensors to measure affect and measure the user state. So we've got one of Roz Bricard's skin resistance watches, we've got a heart rate strap, we've got a facial expression analyzer, things like that. And we're trying to close the loop between the user state and what the room is doing to try to regulate them. So here's a conceptual, and of course the room responds different ways. Here's a video that Asaf has done. He's actually made this thing work open loop. We're closing the loop now as I speak, actually back at MIT, doing the closed loop studies. So a day at the office, he's got a load. His life is a little different now, and there's more work. So the room responds, it senses this, and tries to bring him into a better state. So ideally he calms down. The room recognizes that, and once he starts working, it brings up a more productive environment for that. So the rest of the video just shows the sensors basically working. They're taking the data is all coming in. The data is validated now. It works pretty well, and we're doing the control. When you get to the wrist, you can get to the fingers. We've got a bunch of projects in my group over the years that have been trying to track finger position from the wrist. This is one of the first ones. It was an RFID tags. Here we're using Josh Smith's WISPs, zero power RFID sensors with accelerometers on them with a magnetic read switch to get click with the thumb. The idea again is that your hands are down by your side. I don't like systems that require you to have them in front. You've got your wearable and you'll just do various things to control it. This worked as a proof of concept. They could be made much smaller, lots of ways to shrink the system down, run at a lower power, bring the antenna back up. That's a whole other talk. But my students didn't want to continue doing this. They don't like rings or anything on the fingers. Even though some of them wear rings up here, my Irish student was always wearing them. They don't want anything on the fingers. So we have a bunch of projects to look at this. This is actually David Way's 3D camera to look at finger gesture. Here at MSR, actually, you guys did a laser projection on the fingers to do something similar. Here we did it with a 3D camera, which is going to be ubiquitous at some point when they start getting put into mobile devices. So he did a whole gestural language based on finger lifts and pinches, and you can actually even text with it if he wants. And then Artem, who's interning here at MSR this summer, built a very, very low power pressure imaging band on the wrist to get the images of the tendons as you squeeze your fingers. So this could be on a very, very low power. You run machine learning on it, rapidly initialize it, and it's fairly fairly accurate once you train it. So very low power. You can put it in a watch band. It recognizes pinch gestures of various sorts. You can even recognize if you're carrying things too. He's got a very low power wake up gesture too. If you do this, you can recognize that usually at very, very low power. This is my favorite application of his. It just kind of does this, right? You just put on your brakes, it knows that, and it can flash your brake lights. Artem then went on to form a collaboration with Chris Schmantz guys to develop a fingernail. It's a fake fingernail, which is a full touchpad, Bluetooth. So the whole thing just fits on a fingernail. Battery lasts about 3 hours of constant use. And we showed this at Kai last year. So you can swipe, or you can, it'll find the centroid. You can draw. So your fingernail now becomes a source of input. My students that are doing the lighting work really got interested in wearables. This won one of the awards at the Wearable Computing Conference last year. Nan and Gershon did something they call Halo. So it's a personal wearable lighting system. So you completely change the way you appear to others by how it's illuminated. And he's got a bunch of presets that he can select. So one of Gershon's colleagues comes in a moment. There he's feeling mysterious, I guess. So there's Juliana with her rig. So now they can synchronize. I never knew my students were such actors. They miniaturized it. This is the latest version, where you basically have the LEDs integrated in something more like a set of glasses or goggles. And some of our sponsors actually want to make this, so this could start to be a product. But again, it changes the appearance entirely. Katia Vega has been postdocing in my group. She comes initially from Peru and Brazil. She's the world's authority pretty much on smart makeup. So going beyond wearables to on-skin interfaces before you have implantables, she paints it on the skin. And this is a fashion show she did in Brazil just before she came. It shows what she's doing. So here's her model. And this switches on the eyelids. Strain gauges on the eyebrows, and a switch on the lips. It's taking wearables to a different level. This is her latest thing. No one's seen this yet. They just made this video. I just saw it. Submitting it somewhere. So this is a lighting panel for your back. They call it Scrin. It's a responsive lighting panel. So it changes in different ways depending on context and things like that. Some of you may know I like to build synthesizers. This is my modular synthesizer in the back. I've never seen it used for such a provocative purpose. A little bit about robots. We did work years ago about parasitic mobility, the idea of robots, somebody's choosing to wear you, right? So the robot senses somebody nearby, it decides to attach, and it decides to detach here when it sees light. So you're harvesting mobility, not energy. The robot decides, or the sensor decides it wants to wear you. You don't decide to wear it. This is another one that works off of adhesive. So here she sits down in her chair. It's a silicone adhesive. It attaches to the fresh bond, which is her jacket. So she can move the robot or the sensor somewhere else. So here she's moved the sensor to another location. And again, it likes the fresher bond. So she gets up. It's happy to stay where it is. But it also actuates. It's got a pager motor, so it can decide to fall off if it wants somewhere else. This theme was taken a little bit further by Artem. No one's seen this yet. This is going to appear in WIS, so this is a fresh video. You know, if you have things on you, I showed my little parasitic mobility before, but you know, God knows insects, they're usually not there for a good purpose, unless they're there accidentally, in which case it's still not a good purpose necessarily. But what if they could be doing something good for you? So Artem has made robots that can navigate on clothing. So this is going to be shown at WIST. Here's his little robot. This is in collaboration with Seth Ulmer at Stanford. So the robot navigates with IR beacons you can put on the closest, like a button, or capacitive beacons you can put in. It does dead reckoning, so it already does pretty well by itself. It's got an IMU on board as well. So it can crawl pretty freely through clothing. And he's got a bunch of applications he's done with them. So here's a motion capture. The idea he's trying to do here is that the sensors go to where they want to be in the clothing for their purpose. So in this case, motion capture, they go to places where they'd be suitable for that. And then he just uses his IMU, and he can capture your motion. So now he can move around. So that works. And there's one more segment in a second. So that's, again, just a IMU capturing his motion. But they've decided to go where they want to go for ultimate use. Here's one that has a display that goes to the wrist, and you've got a watch. Or you can have a name tag. We all have name tags, right? And they can decide they need more pixel space. So they find each other, and you get a big name tag. There's more that they've done. You'll see it at WIST. I'm just about done. He's done sensor tape as well, thinking of sensor networks as a material. So you embed the sensing in a material, and we're inspired by tape. You could just reel it off, cut it, put it on the back of something. It becomes a sensate object. He's showed it at WIST last year. He's used it on lots of things, including wearables. So that's the idea of the sensor tape. It's got IMUs on every node. It's got proximity sensors. You can put pretty much what you want, depending on the power level you want to run at. So now it's essentially a shape-determining tape. And he's done applications as touchscreens with the proximity. That's straightforward. But then he uses it to get size. But he does use it as a wearable in the end. In the Media Lab, we wear everything sooner or later. So he takes his tape, puts it on his shirt, and now you can see his posture. I've had people email me one to use this for posture. There's simpler ways, but it does work. So that's about it. Very quickly, some of you may have seen this article. We're all about trying to take sensor information from the real world and then pipe it into human perception in different ways. People have been working with augmented reality with this kind of thing for a while. I think we can take it to a whole new level with all the embedded sensors that are everywhere. This is a cranberry bog in southern Mass we've been working at. It's being restored to nature. It's huge. We're putting sensor installations at 3 locations. Already have about 100 to 300 sensors out there. These are the sensors measuring various things, using them for work with the ecologists. Also audio, we've got about 30 microphones as well. But we're intrigued by what you can do with a wearable. We also bring it to the virtual world. I would do this demo live, there's no time, but if you go to tidmarsh.media.mit.edu, you can download it. You can see the sensor information manifesting as music and as graphics. You can move around in the space as you desire. But we're intrigued with a wearable. If you're looking across the pond, it sees you're paying attention there, start fading up sounds from microphones or from sensors that are making audio over there. You look underwater, you can start fading up sounds from hydrophones. So we're trying to build this. We call it a wearable sensory audio prosthetic. So it's bone conduction, leave your ears open, full IMU, ultra wideband with infrastructure for precision location, falling back to GPS where we don't have it. And again, spatial audio from wherever you look. We're deploying this now at Tidmarsh. But my student Gershon couldn't wait. This is the last thing I show. He made his own wearable. So it's a set of parabolic microphones he controls with joysticks. And it actually works. So here he is walking out of the Media Lab in a Boston winter. And some people are amused by it. Okay. So again, you guys know most of this. It's an exciting time. I think we're midway through this, well, at least the beginning of this wave of computing. Before we go to implantables, I think there's still a lot of fun left to have. So thank you.
Hello. Thank you so much, Professor Joe. It was a wonderful talk. I think we have time for a question or two. I believe there was a question over there. In the middle of the talk, no?
I was just wondering how the rovables, I think you called them, decided where to go on the body. It couldn't be based on the sensor data they were gathering for whatever application. It had to be location-based, based on
Yeah, it is. They can navigate on the clothing. Now, that depends, again, on how it's folded. You may need a map of what the garment is. But they do dead reckoning together with IR beacons at this point. He puts IR beacons on the clothes. You have a button emitting IR, and it can basically try to image that and use that as a fixed point, then do dead reckoning from there. Dead reckoning, if he goes over a shirt from here to here, he can be off by about 3 centimeters. So it's not terrible, but it depends on the fabric and other areas. If it turns, it can get a little bit worse. So you need some sort of way to reset the estimator.
Okay.
And again, they go to where they want to go for their purpose. So the navigation is, they want to go there because they want to go there to do something. And how they get there, you need some infrastructure in the clothing to guide them.
Yeah, I think it's beautifully done. I was just wondering, making sure it was like body diagram based instead of the sensor data they were gathering, and it seems so based on
it has to know about the
point.
clothing it's crawling on and where in the body that represents.
Okay.
Of course, that can vary a little bit depending on what's going on with the clothing, but it doesn't work with spandex as well. Worked very well with this shirt. If I had brought some, I could demo that. Don't know how comfortable they'd be at this point, though.
Thank you so much.
Thank you.
So any more questions? Okay, if you don't have any more questions, let's thank Professor Paradiso.
Thank you.